All right, so today we're going to be talking about evaluating model fit specifically for classification models. So our agenda, we'll do a logistic regression quick review, or maybe not so quick. We'll talk about confusion matrices. We'll talk about the sensitivity and specificity trade-off. We'll talk about area under the curve, specifically ROC graphs or ROC curves, and then we'll do this stuff in code. So be forewarned, this is like a really dense lesson. And if you have a lot of questions, that will be normal. The way that we'll approach this is rather than a lot of bombarding questions on the way through, I'll note when questions will make most sense. In other words, a lot of things will explain themselves in groups of slides. So breaking it up with questions will sometimes not help the flow of this lecture. Nonetheless, of course, always interrupt, and I will either punt and say we're about to talk about that, or answer it on face, or defer to office hours. Cool. So first and foremost, a quick review of logistic regression. So logistic regression is a modeling tactic where our dependent variable is bound in the sample space 0 to 1, and our distribution follows a logic model. So an example of what this would look like plotted is something I've included here, where our model output is either predicted to be one of these values or not that value, 0 or 1, either one of the values or the other value. Critically, even though our sample space is bound by 0 to 1, we do not only output values that are equal to 0 and 1. We receive values that are between 0 and 1. So if we have some model, the output for that model based on some independent features that we give it will be something like, we'll say 0.3, bound by 0 and 1. In that case, we would prescribe that inputted features likely indicate we're dealing with whatever value we've determined or class we've determined to be associated with 0. So to generalize a bit, anything from 0 to 0.49, we will default generalize to be in class 0. Anything from 0.5 to 1, we will generalize to be a part of class 1. So if you think about going back to our example of classifying people based on responses to a survey that they gave, and we're classifying them based on party identification, let's just say for sake of simplicity, it's only Republican or Democrat, and they have 10 questions. The way they answer those 10 questions will not immediately neatly map to fully Republican or fully Democrat, right? There's some things that could be in between. Like someone could both favor more socially liberal policies and favor more fiscally conservative policies. And that person, our model is going to not neatly, of course, be like, oh, that's a 0 or 1, but maybe that's like a 0.6. And the key thing to think about here is we can determine the threshold at which we think that outputted value belongs in which class. So the default is always going to be 0.5. The 0.5 and up, we're going to say class 1. 0.49 and down, we're going to say class 0. There's nothing that says we have to do that. In fact, when we do our model outputs, as we just saw in that notebook, we had a value of 0.8. We can interpret that however we want. Potentially, and most logically, you're going to interpret that to be whatever class is at class 1. But you could also only consider things that reach a certain threshold to be truly a part of class 1, and others that don't meet a certain threshold to not be a part of class 1. And why we would do that is what we're going to discuss at length today. it makes sense to just, classes, they cut it off at 0.5 and call it good. Now, from what I just described, let's switch it up and do a healthcare example, because that's what often logistic regression is used for. In the space of healthcare, you could be predicting that someone has a disease or cancer and have them take a test. And that test outputs whether or not they think they or that individual tested positive or negative for cancer, right? Is our test, our cancer detection tests always accurate? No. Do you see potentially the problem with saying everyone that tests positive most definitely has the disease we're seeking, or everyone that tests negative definitely doesn't have the disease we're seeking, right? It's a very valuable decision about being aware of testing outputs. And so we can plot our sample space, our outputs from that model in something called a confusion matrix, which is aptly named. It's really not too bad. So as I've drawn on the board here, we could have yes and no. They do have it, they don't have it. And how they tested. They tested yes, or they tested no. And you can imagine we can fill this matrix in with our model's successfulness, because in the practice of building a model, we know the true value. We know truthfully if that patient has cancer or not. And we can run that individual's features through our model to see what our model will say about that person having cancer or not. In other words, we can find when our model says yes, but the person actually does not. Or conversely, when the model says no, but the person actually does. We can also find when the model says yes, and they truly do, when the model says no, and they truly don't. And we can plot that accordingly in a confusion matrix. So let's work based off of this one in this slide. Let me ask you to see if there's comprehension about what's going on there. How many classes are there? Two? What are the classes? Yes and no. Yep. How many patients? How do you know? Yeah. And how many times is the disease predicted? How did you get that?
Added up.
So you added up. Yes. Everyone with that? And how many patients actually have the disease? How many did you say? 105. Yeah. They might have just said 5. Yeah. So yeah, you guys grasp what we're seeing here. So let's introduce some terms. So we have true positives, true negatives, false positives, and false negatives. And you guys have all heard of these things before. So a true negative is the person truly does not have the disease, and our model predicted they do not have the disease. In this example, our true negative value is 50. We could have true positives, which is actually they do have the disease, and our model predicted they do have a disease. In this case, that's 100 patients. You have false positives, which are, we predicted that the person has the disease, but in reality, they do not. Which column does that describe here, or which cell? Yeah. False positive. Predicted yes, actual no. And then last but not least, false negatives, where we predict that they do not have the disease, but in reality, they do. It is falsely declared null. That's this guy. Now, two metrics, two keys to success, if you will. The first is accuracy. Overall, how often is this model correct? And without looking at my notes, how would we calculate that? Yeah, so the how often our model was true and accurate in its prediction. So true positives and true negatives. The model said no, and they correctly did not. So true positives and true negatives summed, divided by the total number of observations. So think about it like we had a sample space where we only had a model that said, yes, they have diseases, and they were all correct, and no, these people do not have diseases, and they were all correct. We would have values equal to 0 for any false negative and false positive, and the accuracy would be 100. Any single time someone took this test, we knew our model was going to be accurate, as in sum of true negative, sum of true negative and true positive, divided by the total is going to be the whole, 1. The second thing is misclassification. How would we calculate how often our model is wrong? Yeah, you can either just do accuracy, 1 minus accuracy, or if we just want to do it from the table, what values would we use? Both of those. We want, yeah. Oh, right, yeah. Yeah, so we want every time our model is incorrect, which are the false positives, because it said yes, the model predicted yes, and the actual was no, and false negatives. It predicted no, and the actual value was yes. Both those times, our model was wrong. We sum those two and divide by our total number of observations to get how often our model is indeed incorrect. Here's type 1 error is a false positive, meaning the doctor tells a male that he's pregnant. They took the test and it wrongly said yes, but in reality the answer is no. Or type 2 error, going to be make the wrong decision of guessing when someone's pregnant, is false negative. So in this case, the doctor is telling someone she's not pregnant, but in reality, we are going to dangerously assume that she looks pregnant. Not recommended. So we understand false positives, false negatives, and so forth. There's 2 metrics that are particularly helpful in describing how good our model performs. Sensitivity is when the actual value is positive, how often is our prediction correct? sensitivity is the rate at which our model accurately says yes. How would we calculate that? Over total what?
The row of actual yeses, there's really 105 people that actually have cancer, 100 of them got right, so we take 100 over 105.
Right. So, not n, but instead, it's only the rate of successfully saying yes, which implicitly means how many total times we said yes is the denominator, and how many times it successfully said yes is the numerator. The rate at which, of the times our model said yes, it was correct. So rather than dividing by the total, we only are caring about accuracy of saying yes in the world of sensitivity. So in this case, how would we calculate it?
100 over 105.
Yeah. The actual yes and predicted yes. So we're only dealing with actual yeses in the world of sensitivity. Our model correctly got 100 of them, predicted yes, and it was actually yes. So that's our numerator. And then the total amount of times that the total number of people that are actually yes is the sensitivity's denominator. So if we want to calculate the rate at which our model correctly says yes over how many people actually have this disease, we need to divide 100 divided by the total of yeses, which is 105, and we get 0.95.
If your model was just yes, like it just said yes all the time, then you would still have the same rate based on that calculation. The only thing that would change would there would be 0 in the predicted no's, actual no's, and then all of those would shift right.
Yeah, you're literally 4 slides ahead. Exactly.
Oh, sorry.
No, like awesome. That makes me happy. Yeah. So hold that for a second, and then we're gonna waltz into that. So yes, exactly what you said.
Okay.
Specificity is when the actual value is negative, how often is our prediction correct? So how would we calculate that one?
Negative over negative.
Yeah, so we're only dealing with actual no's, and we want to know the rate at which our model correctly found those actual no's. So the total number of actual no's is 60, but the predicted number of actual no's was only 50. So the rate at which our model said actual no divided by the actual total number of true no's overall, 55 by 60, so 0.83. And going back to the question that you just raised, what is the relationship between sensitivity and specificity? Inverse. Why?
It's a trade-off, right? Like if you had a model at the extremes, if you had a model that always said no, you would have the same specificity rate, but your sensitivity would be completely off. Whereas if you always say yes, your specificity is going to be like more accurate, but your sensitivity is going to be a little bit off. So, like somewhere in the middle, they have to meet, and so it's not as you get more extreme with both. It's as you get more extreme with one, the other goes in.
Yep. So we'll walk through that in a moment. The next thing is the false positive rate, which is just the actual value is negative, how often is our prediction wrong? So false positive rate, so it's just the rate of false positives. So it's just false positives divided by actual no's. False positive rate, the rate of number of false positives. And the rate is relative to the total number of actual no's. Sensitivity is also going to be called recall. And in the code that we go over, recall will be the term to which sensitivity is referred. So recall is the rate at which a value that you're predicting is correct divided by the number of true times that value occurs in your data set. So the recall is the rate at which our model says yes or no. So let me do it relative to the yeses first. So you can do recall for yeses is the same as sensitivity. It is the rate at which our model says yes divided by the total number of true yeses. Recall for negatives is specificity. So the number of times our model predicts no divided by the total number of actual no's. Specificity and sensitivity are easier to work with simply because recall requires you to note which area you're talking about. Like you notice even when I was explaining it there, I had to be very careful to talk about it in the context of yeses and then shift to talk about it in the context of no's.
Right, so there's not one overall recall value.
Recall is relative to the value that you are recalling, basically. Other questions about this? Okay.
Is false negative rate, is that ever anything that matters?
It's calculated the exact way that you envision, and the reason that it's often less important is because we care about, not that it doesn't matter, but we care about oftentimes, and this is contextual specific, minimizing the times our model incorrectly says yes. Incorrect no's are also very important, and we'll talk about that in the context of like disease detection and stuff. And calculated the exact way you would believe. An important metric. However, 4 things you should be concerned with: sensitivity, specificity, and then false positive rate. Okay, so let's say we have this distribution. So this is where you are not allowed to scroll ahead on slides. In other words, scrolling ahead on slides will hurt your own understanding. There. So we have this distribution. Where the left side is these people do not have the disease, and the right side is these people do have the disease. And this is the number of observations, or the test point for these two. So at 50, it's about here. Given this distribution, what value should we choose where at that value we say round up, and below that value we say round down? In other words, if you remember at the very beginning logistic regression, the review, I noted how we get outputs that are bound by 0 and 1, and we can choose the points at which we ascribe things to be 1, and then ascribe the points at which they are classified as class 0. In this case, what test value would you choose to optimize where the cutoff is yes or no? 50. Why?
It's actually going to be right around the exact time in this case. It looks like because all the people that don't have disease are testing the blood and do have disease and drug disease. So we can cut it off there.
So what she said was, correctly, if we cut it off at 50, any test value our model outputs that is lower than 50, it's going to say they don't have the disease. And we know that this is the true distribution of our data in our training set, and we would know that would be correct. We would know that if you're below 50, you don't have the disease. We would know if you're above 50, the model would say you do have the disease, and it would be correct. How do I know it would be correct? This is our underlying data. This is the truth. So I take an out-of-sample data point, and it's 60, and if I had matched that against my training set, which is these guys, I would say, yep, has a disease. And I would be remarkably accurate as per this distribution. It'd be really hard to mess up classifying someone when they're so neatly in their respective sides of the cutoff points. So if I were to shade this, what cell does this correspond to in our confusion matrix? Oh, yeah, excuse me. Yeah. Where does this correspond to in my confusion matrix? This being the area below does not have the disease. I think you guys know. No one wants to say it. True no. True no. Predict no. That would correspond to the upper left-hand quadrant. And where would the area below this distribution that do have disease side of things? And what about these guys? The two that we've not filled in, as in false positive and false negatives. They're empty. Why? Yeah, you're always right. It's a perfect test. You would never predict someone does not have the disease when in fact they do, because based on our underlying data, we can choose a cutoff point wherein those values never overlap, and we would never incorrectly say you had the disease when you didn't, or you didn't have the disease when you do. As you can imagine, this is not the data we see in the wild. So let's talk about how we deal with that. Now our distribution looks like this. Where does not have the disease, still on the left, and does have a disease is on the right. You'll note that the normally distributed values overlap near the long tails of those respective distributions. So, same exercise. Where would I draw the cutoff point to be most accurate? Middle. Right there? Yeah. Now, where does this correspond to again? This area? This one? Bottom right. What about this area? The area where do not disease crosses the threshold of our cutoff point. What is this? Why?
You're predicting that they have a disease or something don't have a disease.
Right. So this area where do not disease crosses our threshold of the cutoff point that we determined, all of that area is, we said, look, that value, any value in this space is greater than 50. So our model says, yep, that's the disease. And the truth is they don't have the disease.
Some of the points that are-
Yeah. But we're talking about like strictly this distribution. So we know they don't. The overlap, you're right. So these are all false positives. What about the area where does have the disease, crosses beneath or below our threshold on the left side? What is that? False negatives. So that means we know someone in this distribution of does have the disease, and their test value was below 50. So the way that we made our model, we said, nope, they're below 50, they don't have the disease. However, the distribution, underlying distribution says, yes, they did. So that was an incorrect, false negative. Right? And so, conceptually, the closer these distributions get together, the better or the worse? The worse. Why?
More overlap.
Yeah.
More error rates.
Yeah. Yeah. The more ambiguity, the more error rates. It's more difficult to determine and parse out if some point is a false positive or a false negative. Now,
Just a tactical question. If we in general would we want to try to minimize? Do we have a hard and fast rule for which area we want to minimize? Because I feel like it could pick up a case where the error rate for false negative is so much worse than a false positive. I think maybe we want to minimize that even if there's a lot more overlap with false positive.
what example are you thinking of?
Well, if it's very costly, if it's a disease where your time to live is very short, you can't catch it. It's very costly to that person. If they thought, oh, you don't have that disease, and it turns out that they do.
Yeah.
I mean, costly in the sense of lost life.
Yeah. Yeah. So you're getting at something that we're about to talk about.
More like study design, like experimental design.
Yeah. Yeah. And so our model design, we hear a good point. We hear, isn't there a time where we might care more about minimizing false positives or more about minimizing false negatives? The answer is yes. From anything from spam detection in your email to cancer detection in patients. Let's think about it in the context of email. In email, would you rather have a spam email end up in your inbox or an email from your inbox end up in spam? Spam in the inbox. So which way did you, where spam detection does, this is spam. Which way do we want to err?
Minimize false positives.
Yeah, we want to minimize false positives. The number of times we think something is spam, we say it's spam, and it's not. So, with that in mind, what about with a costly disease, where diagnosing this disease is incredibly important because it causes restrictions and predictions on the amount of time someone has remaining? The opposite. You probably want to minimize false negatives. So let's think about in practice how we would do those things and how those play into our specificity and sensitivity. So before we do that, what is the area below our does have the disease full distribution? All of the area below that distribution is sensitivity, specificity, neither, false positive. What is it? Yeah, it's true positive plus false negative, which sounds like what? That's related. We have a specific term to describe the distribution below us saying yes versus how many times it was yes. Sensitivity, right? Sensitivity is
Oh, so not the whole area, just the area up to the, or from the line onward.
all of it. The whole area of
The entire prediction.
The whole area under this curve would affect horizontal that every single person actually is yes.
Yeah. And the sensitivity is gonna be, yeah, that's the sensitivity,
Yeah.
not the whole, so the whole area under the distribution would be the sensitivity plus your false negative.
right.
Yeah, okay, right.
So our sensitivity, as Caitlin correctly says, is everything below does have the disease up until this cutoff point that we determined. Because, let's think about what that is. That is saying the true positives and the false positives, and we divide that by the true number of actual yeses, the whole. That's how we get to the sensitivity. So how many times correctly we say yes, divided by how many actual yeses there are, which is why I think you and I just had that moment of confusion for the denominator.
Yeah, it's just the under the whole curve versus after the line, yeah.
Right. So what is specificity then? Specificity, definitionally, is the number of times we accurately said no, true no's, true negatives, divided by how many actual no's there are in our distribution. So this area divided by that whole distributions area, right? So return to the email example. We would rather have spam in our inbox than real email in our spam filter. So how would we adjust our cutoff point.
Move it all the way to the right in this case to increase the specificity,
Which is,
which is the rate of true negatives over total actual negatives.
does that make sense to everyone? And the rate of, in the case of email and spam detection, we would rather find true negatives and put spam in our inbox. False negative, where this guy's spam, this guy's true. So green is spam, blue is real email. We would rather increase the rate of spam that goes into our inbox at the cost of having real email end up in our spam folder. So we would increase the specificity, which decreases the sensitivity. Let's take another example. Let's say we have the cancer detection example. And our cutoff is 50 right now, but we inch it over to So what did that do in terms of our confusion matrix? What values increased, what values decreased, what went on? And why would we do that? So our rate of true positives has increased because we're touching more of them at the cost of what? Yeah. So in other words, we could take this to the logical extreme and catch all of the people that have the disease. We've successfully built a model that catches everyone with the disease. At what cost?
Putting a ton of people without cancer.
We're telling everyone they have cancer. Literally, you take this test, you have cancer. But hey, we caught everyone.
Yes.
It's gonna be your foods.
Just figure out too Medicare fraud with that.
Medicaid fraud.
What's that?
It's called Medicare fraud.
Yeah. Just if you're a data scientist trying to engage in Medicare fraud, there's turn off the recording. Yeah, you see here, we have correctly found everyone that has cancer, but we've also told everyone that doesn't have cancer that they do have cancer. So that's not so good either. And therein lies the trade-off, right? All right. So we've covered a lot. Good. Dial it up to 11 real quick. We know that sensitivity and specificity have what kind of relationship? Inverse. What? How do you know that? Yeah. So in this case, what happened? What went up? What went down? Where we had the original cutoff point of 50, and then we moved the cutoff point all the way to the left. Yeah, sensitivity went up at the cost of specificity decreasing. Second thing that's important, not only do the two trade off, but we don't necessarily know the underlying distribution of all of data of what we're predicting. We know the underlying distribution of what we have, but even that could be non-representative. So with that in mind, we of course want to increase accuracy, but we also want to be cognizant of building a model that respects this very trade-off. Meaning, we can choose a cutoff point that maximizes accuracy, and we can measure the relationship between specificity and sensitivity at that given point. at that given cutoff. So sensitivity and specificity have an inverse relationship, as we just found. So you dial up one, the other decreases. In this case, as you increase specificity, sensitivity goes down, or you increase sensitivity, specificity goes down. And what we're going to do is we're going to say 1 minus specificity, so we can work with a curve where maximizing the area under that curve is a good thing. Let's talk about that for a sec. So sensitivity and specificity. We just plot them. One of them goes up, the other goes down, like that. If we did we did 1 minus specificity, what's the shape of this? So this is called the receiver operating curve. And it allows us to look at these two things so that they move in the same direction, as in moving up and to the right is absolutely a good thing. Which means, as we compare our true positive and true negative rate, we can find values or cutoffs that produce sensitivity and specificity curves that maximizes the area under this curve. So how can we have different curves, all that? So for any given value of accuracy, we have some given sensitivity and some given specificity. We can choose some that are give sensitivities and specificities when plotted that produce curve A, or some that produce curve B. We obviously want to maximize those two, and curve A would be superior in this case. Second thing, because the underlying distribution of our data is not simply like two rectangles, right? They're assumed to be normally distributed, which is what happens when you get high values of some kind of data. It becomes generally normally distributed. So think about how that impacts us moving around this guy, right? When you move this guy around the cutoff point, the increase of accuracy, or rather the increase of sensitivity, comes at increasing rates of trade-off with specificity. In other words, if we were here and we move to the left, we've decreased specificity by a greater degree. Take it to the logical extreme. We're in the exact middle. We're at 50. And we move our cutoff point all the way to 0. So we're saying everyone has cancer, right? We've successfully captured this green area, but at the cost of all of this specificity area dramatically increasing at a higher degree. Do you see that? The trade-off is not 1-to-1. The trade-off has diminishing returns for one and increasing returns for the other. That relationship is exactly why we can produce curves of different shapes and of different qualities. Some curves will minimize the sensitivity and specificity trade-off better than others. And linking it all the way back to the start, that all depends on us choosing some value of the cutoff point in our logistic regression. You choose some cutoff point in that value, that affects your sensitivity, that affects your specificity. Those sensitivities and specificities can be plotted against one another, and we plot them in a way that is useful to us, where you do 1 minus specificity, such that maximizing area under here is a good thing. Sensitivity and specificity don't trade off just 1-to-1. So there's an optimum curve to be found, and that optimum curve depends on the value of cutoff. So the ROC curve is comparing the sensitivity and specificity for a given cutoff point test value in our data set. There's some test values that perform better than others, and even there's some choices we may make that cognizantly make this better or worse at the sake of finding more with cancer or more emails that are ham instead of spam. Now, to illustrate the difference in these curves that we could produce, let's imagine that we're producing ROC curves for various distributions of our data. So in the case of our data with wholly disparate distributions, you guys see if I write over here? Right? In that case, where do we choose the cutoff point again? 0.5. And the area, the sensitivity and specificity trade-off is going to be high or low? What's that? I guess that's kind of a poor question. Yeah. Yeah, so let me rephrase that. That was a badly asked question. That was a poorly phrased question. Given a value of 0.5, are we going to have a relatively successful or unsuccessful model? Is the first question. And the answer is successful. We proved that already. And secondly, how does that impact the area under our sensitivity and specificity trade-off? For this given distribution, we would be able to capture a high number of, almost, we would say all, of the correctly categorized values. Which means if we made some curve, the area under that curve, if it's 100% accurate, would be 1. If we had this case, the curve is going to be a bit lower. We have less area under that curve, and so on and so on. So here's a graphic that's very good on that. If there's no overlapping, maybe there's minimal overlapping at the tails, the area under the curve for our ROC space, radiator operating curve, is 0.9. For this one where they overlap a bit, the area under the curve also decreases a bit because it's generally a bit trickier to identify correctly true positives and true negatives, and that's what sensitivity and specificity are doing. They move them closer together, the relationship continues and gets harder. They're completely overlapping. They are one and the same curves. You put it right in the middle, and the area of the curve is going to be 0.5. Because you're equally uncertain or certain about having a value that does not accurately fit your data. Other questions about that?
Maybe I'm getting hung up on something that's not too important, but if we could go back to the ROC curve, I don't understand why the concavity is like upwards instead of downwards. Like I would think that if we take y minus the specificity, it would be like angled the other way. Like I just don't get why the curve is like that.
Like this?
Yeah, instead of like that. Does that make sense?
Yeah, and I would encourage you to actually play around with values rather than most anything to solve that problem.
Okay.
But yeah, so this makes sense, right? As one increases, the other decreases. So if we do 1 minus this one,
Right.
we're getting a value where a high sensitivity.
It's gonna be 0 there. Right. I mean, I get the 0 over there and the 1 maybe up there. But like in the middle, like if you go over, like let's say going on down to 0.2, then 1 minus that would like be like 0.8.
So
It just seems like the rate of change of the top is like really small and now it
go back to this diminishing returns thing that I was talking about. As we increase one, it's at the cost of the other. And that is represented by a increasing at a decreasing rate concavity.
right, okay.
So that's exactly the shape that we see.
Okay, I think you're right. It becomes
Okay. Let's take a short break and then we'll jump into the code.